Now that we know how to find derivatives using implicit differentiation, it opens up a whole world of application problems we call related rates problems. And we're going to be finding equations in a word problem and then taking the derivative of that equation using implicit differentiation. We're going to switch up the notation a little bit. Instead of using that prime notation that we were using in section 3.8, we're going to replace it with the Leibniz notation. So we'll be using something dt. And that Leibniz notation is particularly useful because it's going to help us keep track of the units that we're dealing with in the equation. And we're going to be taking the derivative with respect to t on both sides of the equation instead of x, because all of these things are with respect to time. This is going to give us a bunch of different rates that are related. So here's our first related rates problem. We have an oil spill, and for simplicity's sake, I'm going to assume that this oil spill is growing in the shape of a perfect circle. It's a little bit oversimplified, but it'll be a nice, easy problem for us to get our brains wrapped around this technique with. So this tells us that the radius is increasing at 1.5 feet per second, and then asks us how fast is the area increasing at the moment when the radius is 5 feet. So I posted a link in the resources for the week for a GeoGebra applet, so you can play along with that as well. I'm going to hop over there to kind of explain what's going on. When you open up the GeoGebra applet, you can hit play on the radius, and it's going to show you this circular oil spill that's growing as time goes on. And we know from the problem it said that it was growing at a rate of 1.5 feet per second. So I want you to imagine that the radius of this oil spill has a speedometer strapped to it, and that speedometer always reads 1.5 feet per second. Now you can imagine each time we increase the radius by a little bit, you're adding on more area than you did the last time. So if we were able to attach a speedometer to the area, that would not be growing at a constant rate. It's growing faster and faster the bigger this gets. And GeoGebra is making my oil spill smaller. So let's start this over. All right, so the oil spill is growing again. And the problem wants to know, well, how fast is that area increasing? What does the speedometer on the area say at the moment when the radius is precisely equal to 5? So what that means is when this gets to 5, we're going to hit the pause button. And we're going to say, in this brief snapshot of time, when we hit the pause button, what would that speedometer say the rate of change of the area is just at this precise moment? So here we are back on the whiteboard, and I've done the first step of a related rates problem here, and that's just to draw a diagram to help us get our brains wrapped around it. And the second thing we're going to do is try to assign variables to everything that's mentioned in the problem. So the first information they give us is that the radius is increasing at 1.5 feet per second. So I'm just going to label my radius in my picture here. There's my R, right? And that's increasing at 1.5 feet per second. Right, so that's a rate of change, and any rate of change is going to get Leibniz notation in these related rates problems. And the Leibniz notation, you can kind of figure out what you're talking about by looking at the units. The units on that 1.5 are feet per second. That's talking about a radius measure per time. So we're going to say that the change in the radius with respect to time is equal to a constant 1.5. Any rate of change is going to get this Leibniz notation. The thing that's changing is the variable in the numerator. The denominator is always time. So they tell us that dr dt is equal to 1.5. They ask us how fast the area is increasing. So they're asking us how fast is area changing with respect to time. So what they want us to calculate is dA dt. All right, and then the last thing they tell us is how fast is the area increasing at the moment when the radius is 5 feet. Okay, that's going to be what I'm going to call the pause button information, and it's going to be important to differentiate things that are constant throughout the entire situation and what's a pause button information. So that dr dt, that increasing rate of the radius, that's constant throughout all the entire problem. But that 5 feet is talking about when we hit that pause button on the radius. So my pause button information is that r is equal to 5. The next thing we want to do is find an equation that relates all of the variables in the problem. And right now that's just the area and the radius. So we have a formula that involves the area and radius of a circle. We know that the area of a circle is equal to pi r squared. And that's going to be our equation that we're going to take the derivative of. So we're going to take the derivative of our equation with respect to time using implicit differentiation. So I'm going to take the derivative with respect to t of the left-hand side of the equation, and then the right side of the equation. And remember, when we were finding derivatives using implicit differentiation, we would treat y as a function of x Here, all the variables are going to be functions of time. So area is changing with respect to time. The radius is changing with respect to time. So A and R are both going to get that function treatment and that chain rule treatment. All right, so I'm going to take the derivative of A with respect to T. All right, we would normally put A prime back in section 3.8, but I said we were going to replace it with Leibniz notation here. So we're going to call this on the left dA dt. And then we're going to take the derivative over on the right. Remember that pi is a constant. It's just a constant multiplier. It's going to go along for the ride. And then we're going to take the derivative of r squared, remembering that we need the chain rule. R is a function of t. The square is the outside function. So we take the derivative of the outside function, leaving the inside function alone. Then we multiply by the derivative of the inside function, which we would normally say r prime, but I'm going to use dr dt. All right, so this gives us an equation that relates the rate of change of the area to the rate of change of the radius. And then once you've taken the derivative, you can plug in all the information that you know, particularly that pause information. It's going to be really important that you don't plug in pause information until after you have taken the derivative. All right, so dA dt is what they wanted me to solve for in the first place. Pi is just pi. The R, that's our pause button information. We can plug it in because we're finally after the derivative. And then that dr dt, that is always equal to 1.5. So we're going to plug in 1.5. All right, so that change in area with respect to time is equal to pi times 2 times 5 times 1.5. So I'm going to ask my calculator to tell me what that is. So I'm going to say pi, got a pi button somewhere in your calculator. You probably have to hit shift to access it, times 2 times 5 times 1.5. And I get 47.1 and change. So I'm going to say 47.1. And then we're going to put units on this. And again, this is where the Leibniz notation is helpful. So this is equal to dA dt. It's a rate. So it's going to be per time. And in this problem, everything was in seconds. So it's going to be per seconds. But then we have to put what the unit is on the top. And it needs to be an area calculation. Okay, so if distance is measured in feet, then area is measured in feet squared. So we'll say feet squared per second. Just like with implicit differentiation, these problems are hard to get your brain wrapped around at first, which is why we're going to do lots of examples.